I am Mayank Parab.
I am Ritesh Patil.
And I am Shivam Nawale. We are students of Sardar Patel Institute of Technology from Electronics and Telecommunication Department. So this is our mini project for MSIC subject, that is Mixed Signal Integrated Circuit. Our project is a low noise long range PIR central conditioning circuit. In this project we focus on improving PIR sensors signal, how PIR sensors detect human motion, especially over long range distances. Normally PIR sensors struggle with weak signal false trigger, so we designed a circuit that not only amplifies the signal but while keeping the noise extremely low. This is achieved using two-stage active band pass filter and amplifier, which will be explained step by step. The PIR signal challenge. The main challenge in PIR sensor is that they generate extremely small signal, typically in microvolt range. So removing noise from such a small signal is very difficult. These signals are so weak that they are easily affected by noise such as temperature drift, power supply fluctuation, electromagnetic interference. Because of this, simple amplification way is not enough. It can actually amplify noise as well, which will give us fault detection. Our goal to design a system that not only amplifies the signal but also intelligently filters out unwanted component to ensure reliable detection. So moving on to system architecture, our solution uses two-stage active bandpass filter topology. As shown in the diagram, the signal passes through two identical amplification stage and then go through a final low-pass filter stage. Uh, each stage provides 45 dB gain, resulting in a total of 90 dB amplification. Splitting the gain across two improves the stability, avoids distortion, and ensures the op-amp operates within safe limits.
So now we move towards the stage 1 biasing and high pass filter. In the first stage, we start by setting the operating point using resistor R2 and R3, which create a mid supply bias at VCC by 2. This allows the signal to swing both positively and negatively without clipping, even though we are using a single power supply. Next, we implement a high pass filter with a cutoff frequency of zero point 0.7 Hz. This removes very slow variation like temperature drift and DC offset, ensuring only meaningful motion signals pass through. So next one is gain and low pass filter. This stage also provides a gain of about 45 uh, decibels using a feedback resistor configuration. The gain is carefully chosen to amplify the signal significantly while maintaining stability. In addition, a low pass filter with a cutoff frequency of 10 Hz is implemented. This removes high frequency noise such as electromagnetic interference and prevents unwanted signals from being passed to the next stage. So next slide, stage 2 and output filtering. So the second stage is designed to be identically to the first stage using the same component values. This symmetry simplifies the design, reduces cost and makes implementation easier. It further amplifies the signal while maintaining the same filtering characteristics. Finally, we add passive low pass filter at the output to remove any remaining noise before sending the signal to a microcontroller or ADC.
So next is basically frequency response. The graph shows the frequency response of our circuit. We observe a peak gain of around 78.8 decibels at approximately 2 hertz frequency, which matches the typical frequency of human motion. Signals below 0.7 hertz and above 10 hertz are significantly attenuated. This confirms that our circuit effectively acts as a bandpass filter, allowing only useful motion signals to pass through. Next slide shows the noise performance. In this slide, we analyze the noise performance of the circuit. Even though the circuit provides a very high total gain of 90 decibels, the output noise is only 10.29 millivolts RMS. This indicates that the design successfully minimizes noise while maintaining strong amplification. As a result, the system can reliably detect motion without false tripping. Now let's move on to the summary and conclusion. To conclude, we designed a two-stage amplifier system that achieves 90 decibel gain with a bandwidth optimized for human motion detection. The use of proper biasing and filtering ensures high stability and low noise. This results in reliable long-range motion detection with strong immunity to interference and false triggers. Thank you very much.
Let me walk you through the key calculations behind our circuit design. The process follows a specific order because some components directly influence others. We start by selecting the capacitors. For the low pass filters, we chose C7, C5, C9 as 10 microfarads. We begin with capacitors because large values have fewer standard options, while resistors are easier to adjust later. Using a target high frequency cutoff of 10 Hz, we apply the standard formula frequency equal to 1 by 2 pi RC. This gives us a resistor value of approximately 1.59 kilo ohms, which we later round to the nearest standard value of 1.5 kilo ohms for R5, R6 and R11. Next, we designed the high pass section. We selected 33 microfarads for capacitors like C2 and C4. Using a low frequency cutoff of zero point 0.7 Hz, we calculate the resistor value to be around 6.89 kilo ohms, which we round to 6.8 kilo ohms for R4 and R9.
So now we moving on to biasing and gain calculations. Biasing is critically because our op-amp operates on a single supply. We use a voltage divider to set the operating point at mid supply. To maintain the correct high pass behavior, the equivalent resistance must match R4. So we choose resistor values approximately 13.7 kilo ohms for the biasing network. Next is gain. We required a total gain of 90 decibels. So we split it evenly into 45 decibels per stage. This corresponds to a voltage gain of about 178. Using the relation between gain and resistors, we calculate the feedback resistor to be approximately 1.2 mega ohms. Finally, for stability, we place a 15 nanofarad capacitor across the feedback resistor. This creates a low pass effect at 10 Hz, preventing high frequency noise and oscillations. Since both stages are identical, we reflect the same values, which simplifies the design and ensures consistent performance.
Now, let's look at the simulation side of our project.
So this is a simulation file of our project. We have used multi-sim software to simulate our project of PIR sensor. As if we cannot simulate real conditioning of sensors in simulation, we have used a typical input of PIR sensor, which is 2 millivolts peak to peak, and frequency is 7 hertz, which is the frequency of human motion. This will be the typical output of PIR sensor if this circuit is implemented in actual hardware. We have used op-amp LMV358M. As we know the signal is very small, it is 2 millivolts. So we have used this specific op-amp for minimum input bias current, and to work at low frequency. At the first two op amps are of amplification and filtering stage. I had explained in our presentation. We have added an extra stage using op amp 741 to our simulation, so that converts the analog output, which is basically a comparator that converts the analog output of our amplifier and filter stage from PIR sensor circuit uh, into a digital signal. So that gives a digital high and low output signal. So basically, when the PIR sensor will detect motion, it will send signal to a circuit, or it will be filtered and amplified. After filter and amplification stage, the last op amp will convert it into analog to digital signal, that is high and low signal, so that it will be easy for detection. I will just run and show our simulation file. So this is a high time signal of our simulation. Uh, as you can see, as we here sign input, but still our. So now let's run our simulation file and observe our output. As you can see, there are two signals. First signal we are showing the analog output of the amplifier and filter part, and the second output, that is we can show in the form of high and low signal, is the output of the comparator. We are comparing the signal with 3 volt. Our output range is between 5 volt to 0 volt. In case some noise is amplified, for safe side we have kept the reference voltage to 3 volts. As seen in the graph, when analog output goes above 3 volts, our digital signal become high, and when it goes below 3 volt, our digital signal becomes low, indicating is there motion in front of VR signal or not. Thank you.